Here we go.
This meeting is being recorded.
So in section 4.3, we're going to work with conditional probabilities. We're also going to work with our complementation rule. And we're going to start with this one, problem number 29, about medical helicopters used in transporting patients. So a couple numbers to take note of in this one is that there's 47,637 patients that were transported by helicopter, and a little bit more than twice that much that were transported by ground. So a total of 159,511 patients. The first question is, if one of those patients in the study is randomly selected, what's the probability that the subject is transported by helicopter? Well, let me develop some notation here first. Let's let H be the event that a person or a patient was transported by helicopter. So that in essence, problem number 29 here, the first part is asking for the probability of H. Well, what we have to do is figure out how many people were transported by helicopter and divide that into the number of people in this little problem. And I think they actually gave you both numbers outright. So the denominator is given to us right here. That's the 511 right there. So that's our denominator, 159, 511. What should I put in our numerator? No one?
47,637.
Thanks, Don. 47,637. Yay. And there we go. So part A, we knocked that off. Part B is a little tougher. Part A is just going to be this ratio. In part B, they're going to extend this. They're going to select 5 people out of this population and see if they're transported by helicopter. And the question is, what's the probability that all 5 of them were transported by helicopter? Now let's just do a little bit of a check here. Is that 5 people going to satisfy the 5% rule? Well, so 5% rule. If we're looking at 5 people, is 5 people less than 5% of the population? N equal 5 less than 5% of the population. A or nay?
It is less than 5%.
Yeah. I mean, if you wanted to figure out 5% of the population, then that part right there, that's your population size. Call it capital N. 0.05 times N is really 0.05 times 159,511. And that's going to be, I don't know, about 8,000 maybe, pretty close to that. 0.05 times 159,511. Yeah, a little bit less than 8,000, 7,975 and change. But it's certainly greater than the 5. So we can use the 5% rule. That's good. So use the 5% rule to calculate the probability that 5 people in a row are taken out of this study. So it's going to be probability of H1 and H2 and H3 all the way down to H5. So let's calculate those probabilities. So the probability of the first one is drawn and used a helicopter to be transported would be 47,637 over 159,511. Now keep in mind we're sampling without replacement. So sampling without replacement. Technically, we should, in calculating the next probability, the probability that the next person was pulled out of this possibility or this study and flew by helicopter, that should be 47,636 over 159,510. That's what it should be. But what does the 5% rule say? The 5% rule says treat them as if they're independent events. Now, when you're sampling, how do you sample and get independent events? What's the method that we use to sample and get independent events? It'd be sampling with replacement. So if I replace this, then it'd give me 47,637 over 159,511. That's not exactly the right probability, but it's close enough. It's not going to make a big difference because our sample size is so small. And then it'd be again and again and again for the second, third, fourth, and fifth patients. Now, overall, what does that lead to? Well, does anyone want to type that in their calculator for me? Multiply that by itself 5 times? I sure wouldn't. What's a clever way to do this? Multiply that by itself 5 times.
Raise it to the 5th power.
Yeah, raise it to the 5th power. So 159, 511, raised to the 5th power. Yay, and that's it. That's it. So there's your probability. Are we okay with that one? We're able to multiply because we're assuming that they're independent events. So, and we use the 5% rule. The 5% rule is what it leads us to be able to use independent events and multiply these like we did. If we didn't have that, this would be a real pain of a calculation. It's not something I'd want to put into my calculator. This I don't mind. I don't mind doing one of these. Doing 5 of these would be kind of a pain. But let me show you what that would look like if we didn't use the 5% rule. So without the 5% rule, let's see if I can't focus that better. There. Without the 5% rule, it'd be 47,637 divided by 159,511 times 47,636 over 159,510. And whoa, this becomes really tedious pretty fast, doesn't it? 159,509. And 2 more, 47,634 over 159,508. And 47,633 over 159,507. Ugh, Well, we could calculate it, but you know what? It's going to be really close to what we just did. So this is without replacement. And I want to focus in on these two events. Let's just look at the first two of this. Really, that's a probability of H1 and H2. Probably getting a helicopter ride on the first patient and a helicopter ride on the second patient. Now, last week when you're doing some of your practice problems, some of you might have run into a strange formula. And it would have looked something like this. Probability of H1 times the probability of H2 given H1. Wow, that looks bizarre. And so let me tell you what this formula is and really mention that we've already kind of covered it, although we're going to spend some more time covering it here today. So what this formula is for conditional probabilities. Conditional probability. Yeah, conditional probability. There. And let me write it like this. Probability of B given A. Probability of A and B the way you would read this is that it's the probability of B given the occurrence of event A. So what's the chance that B can happen given that A has already happened? Let me diagram that for you and try and help you make sense out of it. So let's do it this way. So I'm going to let that represent my sample space. That's all the stuff that can happen. And then I'm going to have two events inside that sample space. We'll call one event A and the other one event B. Be like that. Now, typically speaking, the probability of event A is the area of A divided by the area of the sample space. No problem. But if I'm looking at the probability of B given A, by telling you that A has occurred, I'm shrinking my sample space. It's no longer just the whole outside of blue. It's just what I have right here. So I'm telling you, you know what? That's my new sample space. And the chance that A occurs is now, or excuse me, the chance that B occurs is now just this little region where they overlap. Just that little piece right there. So it's the probability of A and B where they overlap divided by the probability of A. All right. Some of you might have your head swimming at this point, and I understand that. I'm sympathetic. But the good news is that intuitively, you've already used this formula. Let me demonstrate. Back up here, when we calculated these two probabilities, this one is just the probability of getting a helicopter ride on the first flight. But this one says, all right, what's the probability of getting a helicopter ride on the second person, given that this already happened? So you had to say, oh, well, I took one out of this numerator and one out of that denominator. That gave me that probability. Well, guess what? Calculated the probability that the second person got a helicopter ride given that the first one did. That's what you calculated right there. So in essence, you've already used this kind of a formula, but we are still going to practice it nonetheless a little bit. It's not going to be very often that you're going to be demanded or called upon to use it in this form. You're just going to use this more or less intuitively. And we'll see that. So let's look at a couple of the problems on your handout and see what those have to say about these kinds of things. And hopefully after we do a few, it's not going to seem as intimidating as maybe this first one does. So. All right. Why is this one not scrolling down for me? Okay. So here we go. We're going to work on this one called Denomination Effect. So kind of some interesting research, and maybe after we understand it a little bit, you can identify with it. But students were given either 4 quarters or a dollar bill, and those are randomly selected, and they're offered the chance to keep the money or spend it on some gum. Now, here are the results. Students given the 4 quarters purchased gum 27 times and kept the money 16 times. So let's come up with some marginal totals here to kind of help guide us a little bit. So across the top, that would be a 43. And then second row would be a 36, a 46, for a total of 89. Now let's hope that totaling things up on the bottom gives us the same overall total. So here we've got 39 and 50. And so yeah, both those line up pretty nice. And I'll introduce some notation here so that I can talk about some events. So for instance, Q is going to be the event that students were given 4 quarters. B is going to be the event that they were given a dollar bill. Now, equally likely, or would have meant the same thing, I could have just called this Q bar because it's the opposite of Q, or I could have called Q B bar, but it felt more efficient, a little bit easier to understand if I just used some nice letters for those events. So let's look at the first one for problem number 13, 13A. Find the probability of randomly selecting a student who spent the money given that the student received 4 quarters. So let's see if we can't write that down using notation first. So we want to find the probability that they spent the money. That's event S up here, given that they received 4 quarters. So given Q. Notation-wise, it's going to look like this. Probability that they spent the money given that they received 4 quarters. Okay, let's see if we can't figure that out. Now, at the beginning of the problem, your sample space is this entire table. But that changes the moment that they say that, well, I'm going to tell you that this student received 4 quarters. Your sample space is no longer the entire table. It's just part of that table. Can anyone tell me what part of that table the sample space is? What row or column?
Would be the spent.
Which one?
The spent column.
Wouldn't be the spent column. Because they were what you're being told is that they were given 4 quarters.
Q.
So what part of the table does that put you on?
Q.
Yeah, it's going to be Q, right? It's just going to be all this right here. So instead of dealing with the entire table anymore, now you're just dealing with the first row. You can ignore all the rest. You're being told, you know what? We're just focusing on the people who got 4 quarters. So yeah, that's this first row. Now, of that first row, how many of them kept the money? Or is, let's see, we want to spent the money. So how many of them spent the money in the first row? Or what's the probability in that first row of spending the money?
27 over 43.
Thanks for that. 27 out of 43. So about 63% spent the money. Okay. Now, I'm going to kind of extend this problem a little bit. We're actually going to do some of the problems that are below this, but let's take a look at this. Probability of spent given B. How is that different? What am I saying here? What does that probability mean?
How many spent the money given that they were a $1 bill?
Yeah. So it's the probability of spending it given that you received a dollar bill. Okay. Let's take a look at that one. So you're no longer dealing with this first column here. You're dealing with, or excuse me, that first row there. Where are we on the table then? For the second part, where we're looking at people who were given a dollar bill and we want to find those who spent the money. Where am I at in this table? What should I highlight?
B.
B.
Row B.
Row B. It's this right here. Because you're being told that the students were given a dollar bill. Given a dollar bill. In fact, the nickname of the old mayor of Royal Oak was Dollar Bill. So I think he was a lawyer. In any case, how many people were given a dollar bill?
46.
46. And of those people who were given a dollar bill, how many spent it?
12.
12. Cool. That's a little bit over 25%. So 26%. Now, I don't know if you can identify with this or not, but certainly when bigger bills are in my wallet, I'm more reluctant to break them. You know, 20s and 50s don't leave my wallet as fast as, you know, 5s, 10s, and 1s. Those I'll spend without even thinking about it. But boy, you give me the bigger bills, man. You know, you got that 50 or that 100 in there. That doesn't leave the wallet too easily. You just hang on to those. I don't know. Is anyone else the same way? All right.
Yeah. For me personally, I don't carry cash.
Yeah, that's probably the smartest thing, you know. Do it off your phone nowadays, right?
Yep.
All right. Let's do part B now. And we'll extend part B kind of like we did the other one. This is part B. Find the probability of selecting a student who kept the money given that the student received 4 quarters. So I want you to try and come up with this notation, this one. And by that, I mean for part B, probability of blank given blank. Fill in that notation for part B for me. Find the probability of randomly select a student who spent the money given that the student received 4 quarters. Okay, someone want to volunteer with what that notation would be? What would I write here?
Probability of K and then Q.
I'm sorry, I couldn't quite hear that.
K and then Q.
Probability of K given Q? Did I hear right?
Yeah.
Good. Yes, that's exactly right. Probability of K given Q. So again, you got to think, well, where am I on this table? Where am I?
The kept column.
Good. Well, I see. No, we do want to think about the kept column eventually, but look at the given part. What are you told is absolutely already happened?
Quarters.
They were given quarters.
Yeah, you're given quarters. Good. Thank you, Lauren. And then there was another voice in there too. So you're given quarters. So that tells you you're in this row. You can ignore everything else because you're in this row. You're not looking at the people who were given dollar bills. You're just looking at the people who got quarters. Now, amongst these people, how many of them kept the money?
16 out of 43.
Excellent. 16 out of 43. Nice. By the way, I'll point out that if you use the complementation rule, this probability is 1 minus this probability. So you can use the complementation rule to get those. This is about 27%, or yeah, 37%. Someone describe what this would be. Let's see. No, not B. How about Q? There we go. What is this saying? What probability am I going to try to calculate next? You know what? That's the same thing. How about if I do, yeah, I did have it right the first time. My bad. Probably K given B.
Probability that someone kept the money given dollar bills.
Yeah. So they got the dollar bills and they kept the money. So thanks, Sam. So probability that they got some dollar bills and kept the money. See if we can't figure out what that probability is.
Would it be 34 or 6?
Yes, 34 over 46. So with this one, you're now saying, okay, well, we're working in this row right here. So if you're in that row, there's 34 people who kept the money out of the 46 in that row. So 34 out of 46 is about 74%. So basically, you're more likely to keep the money if you have larger denominations. Quite simple. Quite simple. How are those looking? Now, technically, if you wanted, you could calculate this as the probability of K and B divided by the probability of B. And that's really what the formula would say. And what you would have to do is find out how many people are that kept the money and were given dollar bills. So that'd be 16 out of 89. And then the denominator part of this would be the probability that you're given a dollar bill. So those who are given dollar bills would be 46 out of 89. And guess what? When you simplify this, these two will cancel. Let's see, did I get the wrong number there? Oh yeah. Yeah, this one should be 34. These two 89s will cancel and leave you with 34 out of 46. So it's exactly the same thing we got up above. It's just using the definition. And what I've been telling you is that for the most part, you're not really going to have to use this definition. You can just rely on using the table and adjusting things accordingly, adjusting your sample space. Let's try another one. Unless there's some more comments on this last one. Okay. I don't know why this doesn't scroll for me very well. It's just so annoying. So here's our next table. And I've kind of introduced some notation here. And even though we're already using P for probability, we're going to use P for a positive result, N for a negative result, C for hepatitis, and C bar for no hepatitis. So that's the notation. And we're going to look at some probabilities of false positives, false negatives, that kind of thing. So I'll give you a second to copy down or make notes on them, whatever notation you want. And then we'll look at problem number 17. In fact, while we're waiting, why don't you see if you can't think of the notation I'd use for the first part of this. It says, find the probability of selecting a subject with a positive test result given that the subject does not have hepatitis C. So we want the probability of a positive test result given that the subject does not have hepatitis C. So by the notation, what I'm looking for is this: probability of what given what. What notation should I put in there? Understanding that I've used these letters, P, N, C, and C bar. Does anyone want to give that one a shot? Does anyone want to be the second person to give that a shot? Maybe you decide to be the first person.
Probability of P given C bar.
Excellent. So we want a positive result, so it'd be a P, and the subject does not have hepatitis C, so that'd be C bar. And if you'd like to see it visually, there it is. Probably they get a positive result given that they don't have hepatitis C. So let's see if we can't figure out where that puts us. Now, it might not be a bad idea, kind of like the last one, to write down some marginal totals. So let me do that here. That'd be 337, 1,163. And then, let's see, what, 345, 1155, and 1,500. Okay. Let's calculate some probabilities. So Don got us started. We got the right notation. Let's take a look at what we're given. We're given the event of C bar. So that limits our sample space. It limits where we can be on our table. What part of our table should I highlight to say, okay, this is what we're going to look at?
C bar.
C bar. So basically, this bottom row here. Awesome, thank you. So C bar, that's this row right here. So we can ignore the rest of the table. We're no longer dealing with 1,500 people. We're dealing with 1,155. What's the probability that they get a positive result given that they don't have hepatitis C?
2 over 1,155.
One more time.
2 over 1,155.
Good. 2 over 1155. You've got 2 people that get positive results out of 1,155 people there. Perfect. Now I'll come back and do the second part of this together with the second part of problem number 18. Let's move down to problem number 18. We're going to look at false positives and false negatives. 18 is the false negatives. Find the probability of selecting a subject with a negative result given that the subject has hepatitis C. So once again, I need to come up with some notation. Probably they got a negative result given that they have hepatitis C. So see if you can't write down what that would be in symbols here for us.
N and C.
Awesome. N and C. Thank you so much. Probability of N and C. Let's see if we can't do that calculation. We're no longer working with the yellow row. What am I working with?
345.
Nice, nice. So by understanding that the event C has happened, we're at this row. So we're in the first row of this table, and there's 10 people amongst the 345 who got hepatitis C, yet got a negative result. So, all right. Let's take a quick look back at these two follow-up questions. Why is this case problematic for test subjects? So we're back to problem 17 here. That's the probability of a positive result given that you don't have hepatitis C. What's the problem here?
That person doesn't have hepatitis C.
It's a false positive.
Yeah, you don't have the disease, but yet you're told you do. That's going to cause a lot of stress and worry and follow-up tests. So that's kind of a bummer. Does this look like it's a big problem, though?
No.
Yeah, it's a pretty small problem. I mean, it happens less than 0.2% of the time. A little bit less than 2 out of 1,000 people. So it's not a big problem, but it's certainly a concern, especially if you're applying this test like millions of times. Then there's going to be a lot of false positives. Which looks like a bigger worry, false positives or false negatives?
False negative.
Yeah, false negative looks like it's much more frequent. So if we do that one, 10 divided by 345, a little bit less than 3%, but that's a lot more frequent than this is over here. So this is false positives. This is false negatives. And even though these numbers are small, they each present a bit of a challenge. These people got to get retested and stuff like that. These people, these turn into our super spreaders, like, oh yeah, you're okay. You don't got it. And then they're free to mingle and then can spread the disease around some more. I don't think you can catch hepatitis C socially, but obviously our current situation with COVID is a little bit different. So these are some concerns when you're creating these types of tests. Now that goes beyond our considerations here. We're just looking at the probabilities. Are you comfortable with the probabilities here? Those probability calculations? Because that's the part that I want to, that's the part that I'll test you on, not some of this other stuff. Okay. Let's see here. Let's go down to the bottom. And we'll talk about this one. We're going to flip a penny twice and look at some outcomes. So kind of like the last couple, let me develop some notation. And then we'll talk about things. So just call this a penny example. I'm going to let H1 represent the event of getting ahead in the first flip. The event of heads on the first flip. H2 is the event of heads on the second flip. And I want to calculate a couple probabilities here. Which probabilities do I want to calculate? Well, I'm going to start out with the probability of H2. What's the probability of getting ahead on the second flip?
1/2.
All right, let's take a look at that. And let's see how Don may have arrived at that. So right here, S, that's our sample space. These are all 4 things that can happen. Now, I've also shown you that with a tree diagram. That is, at this first point, you've got 2 things that can happen. And at each branch point, you've got 2 more things that can happen. So you get 2 times 2. So that's kind of a counting procedure that we'll look at in section 4.4. Any way you slice it up, there's 4 things that can happen. Now, of those 4 things that can happen, let's take a look at how many of them, of those 4, have a head on the second flip. So that would be this one and this one. So one way you could do this is say, all right, well, there's 2 ways that you can get ahead on the second flip out of 4 possibilities. And as Don said, that reduces to 1/2. But now, since I'm your friend, I'm your teacher, BFF, let's take a look at this one. Before we look at the probability of getting ahead on the second flip, I want to help you out. I'm going to whisper in your ear that, hey, you know what? We got ahead on the first flip. So that's some good intel that I'm giving you. Let's see what that does to this calculation of the probability. Probability of H2 given H1.
1/4.
Let's find out. I mean, that's a good guess. Well, let's understand something. If I tell you that we got ahead on the first flip, probability, come on. Probability of H2 given H1. I'm no longer dealing with the whole sample space. Let's look over here at our sample space. What part of the sample space am I going to deal with? What half out of those 4 circles?
The left.
Don's voting for the left half. Do you agree with Don?
Yes.
All right. You're wise to agree with Don. Thank you both. These are both the events that show a head on the first flip. So that yellow circle represents our new sample space. So there's 2 things that can happen. Of those 2 things that can happen, how many ways are there to get ahead on that second flip? Just 1, right? Only 1 of these has a head on the second flip. 1 out of the 2. So there's your probability. Wow. So did my news here to you that, you know what, you got ahead on the first flip, did that really make a difference to you? Did that change the probability of a head on the second flip at all?
No.
No, it didn't. And that's because these are independent events. So what happened with the first one has no effect on the probability of the second one. So let's write that down. H1 and H2 are independent events. That's important.
Quick question. How do you know when they're independent or not?
It's a great question. Let me see if I can't. Let me see if I can answer with probabilities. Events A and B are independent if, and I'll give you two definitions. One, the outcome of one doesn't affect the probability of the other. So that's one way. Or if you wanted to write it with notation, that'd be probability of A given B equals the probability of A. That is, if I tell you that B occurred, it's not going to change the probability that A occurs. They'll just be the same. Just like up above in our previous example, probability of a head on the second flip was 1 out of 2. Probability of a head on the second flip, given that you had a head on the first flip, was still 1 out of 2. That is, that extra information didn't change the probability at all. So both of these are saying the same thing. This just says it with symbols. Odette, did that help you with your question?
Yeah, that did. Thank you.
Okay, good, good. Because independent events are going to be something that's important later on. Now, are you going to have to use this to always show it? No, but we will have to work with the idea of being independent. And both of these are good notions or good definitions of independence. Nice, nice, nice. Okay, got a little bit more to finish up in this section, and it's going to be to kind of review the complementation rule and also review independent events. So there is one other nice corollary here that I can write, and I appreciate your question for that. If A and B are independent, so that's assuming they're independent, then probability of A and B equals the probability of A times the probability of B. That is, you can just multiply these things to get their probabilities. So, yay. And we'll do an example like that in just a minute. Okay, let's look at some problems up towards the top of our sheet here. And we'll start with problem number 5 from the top there. And problem number 5 we can do as a nice example of the complementation rule. And then we're going to use what we just learned about independence for problems number 8 and 10. So for problem number 5, I'm actually going to write out the sample space. It says find the probability that when a couple has 3 children, at least one of them is a girl. Assume that boys and girls are equally likely. Well, if boys and girls are equally likely, then the sample space is going to be filled with points that all have the same chance. So let me write down the sample space. We could have 3 girls, girl, girl, boy, girl, boy, girl, and girl, boy, boy. You could also have boy, girl, girl, boy, girl, boy, 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 girl, and boy, boy, and boy. That's your sample space. Now, all of these things are equally likely. And that's only because the probability of boys and girls is the same. At least we're assuming that to be true in this case. Now, the problem itself asks you for the probability of at least one girl. And I want to help you get it, wrap your head around that and start thinking of the complementation rule. When you see the words at least one girl, you should start thinking of the complementation rule. Because let's look at all the different events that would make up the probability of at least one girl. It'd be all of these. So to find the probability of at least one girl, you'd have to find the probability of all girls, 2 girls and 1 boy, boy, girl, etc. You'd have to do 7 calculations. That feels like a lot. So start thinking about the complementation rule. If you use the complementation rule, probability of at least one girl is going to be 1 minus the probability of all boys. There. Now, what's the advantage? The advantage is that that's only 1 calculation, not 7. So it's a lot easier to calculate this than it would be this. In this particular example, we could have done it the first way, but that's just because these points are equally likely. It makes our calculation a little bit easier. The probability of all boys is 1 out of 8. So it means there's a 7 out of 8 chance that you'll get at least one girl. The big thing I wanted to get across here was that when you see these words at least or at most, start thinking of the complementation rule, because it's going to make your life here a lot easier than it would be otherwise. And we'll definitely see that when we start looking at problems like number 10. Okay, let me roll on to number 10. We'll do 8 and then 10. Just to try and get a handle on some of this stuff. So problem number 8. Births in China. In China, where many couples were allowed to have only 1 child, the probability of a baby being a boy was 54.5%. Now, they've since stopped that 1 child per couple policy. I think they ended about 6 years ago. Among 6 randomly selected births in China, what's the probability that at least one of them is a girl? So, okay, at least one of them amongst the 6. Now, writing down the sample space here would be a real pain. And it's not really going to help you much because those points in the sample space aren't equally likely. So I can't just do, 1 divided by however many, in this case it'd be 64, like I did with the last problem. But I still want the probability of at least one girl. At least one girl. When you see that, start thinking of the complementation rule. Probability of at least one girl is going to be 1 minus the probability of all boys. Would it help to see that graphically? That one is the complement of the other?
Yeah.
1, 2, 3, 4, 5, 6. Here we go. I appreciate the feedback. Thank you. So at least one girl. So let's let this be the number of girls. Number of girls. What events here would satisfy at least one girl? Could I have one girl? Would that work here? Yeah, one girl would work. How about two? Would that meet the requirements of at least one girl?
Yes.
Yeah, 2 or 3. Should I stop there?
No, it's all of them.
All of them. All of them except which one?
0.
0. So I've kind of got a dividing line right here. This is event A. That's at least one girl. This would be A bar. 0 girls, and 0 girls is the same as all boys. So my morning class, I had a student who is one of 6 girls in the family. That's really unusual. It's not unheard of, but it's pretty unusual. So instead of calculating the probability of 1 girl plus the probability of 2 girls plus the probability of 3, 4, 5, and 6, instead of calculating all these 6 probabilities, which is, difficult unless you know the right stuff, it's going to be a lot easier to calculate the probability of all boys and then subtract that probability from 1. So I hope that helps. Let's calculate the probability of all boys. So probability of A bar. Probability of A bar. Probability of all boys. That means a boy on the first one and a boy on the second one and on the third all the way down to the 6th. Now, what did I say about events earlier? If events are independent, then you can replace this with probability of B1 times probability of B2 all the way down to probability of B6. And they gave you these probabilities. That's going to be 0.545, 0.545, 0.545. In other words, 0.545 to the 6th power. That's almost what I want. But I want to do 1 minus that probability. So 1 minus 0.545 to the 6th power. Should be pretty high. Should be 90-something%, I'm guessing. But let's just do that on our calculator. I'll do it here so that way you can keep copying. 1 minus 0.545 raised to the 6th power. Yeah, 97.38%. So 0.9738. Yay. Cool. Awesome. How are we looking with that one?
Good.
Thank you. Thank you.
This meeting is being recorded.
So the question is, can we do number 5 without the picture? And the answer would be yes. You're still going to have to realize that you want to use the complementation rule as opposed to calculating all these things directly. And it's going to come down to the probability of a boy on the first one and a boy on the second one and a boy on the third. So what's that? Well, because each of these are independent of the other, I can write that as probability of B1 times probability of B2 and the probability of B3. Now, keeping things simple, what's the probability of a boy when a couple has a baby? 1 out of 2. And then 1 out of 2 again, and 1 out of 2 again gives me the 1 out of 8 altogether. And so then you can put that in here and say, all right, well, it's a probability of 1 minus, or excuse me, probability of at least one girl is 1 minus 1/8, which gives you your 7/8. So is that what you're looking for? Or,
Yeah. Yep. But
okay.
for like the 2, why isn't that like a 3?
Because
Isn't
there's
it like 3
boy or
girls,
girl.
3 children?
No, because
Oh,
each time you're looking at the probability of a boy on that one pregnancy. So there's a 1 out of 2 chance of a boy.
All right.
In practice, it turns out that boys are a little bit more likely to be born than girls, which maybe genetically is a good thing because boys tend to die off a little bit faster than girls. So maybe that's good that we're born at a little bit higher frequency. But it's close to 50%. In China, the 54.5% that we're dealing with, that's pretty high. And that suggests that there's something else going on. But, you know, I don't want to get into a social commentary about China. So, all right, cool. Thank you.
This meeting is being recorded.
So let's continue with problem number 10. You're guessing on the SAT. Now for the SAT, each question has 5 possible answers, and you're going to make 10 random guesses at the SAT. Maybe they say time's almost up, and you're convinced that your best strategy is to just guess the rest of the way. Okay. What's the probability of getting at least one correct out of those 10 guesses? So let's draw ourselves a little sample space. So there's our sample space. And let's just cut it off here. 2, 4, 6, 8, and 10. We want to look at the event of getting at least one correct. So that'd be all these here. That's the event of at least one correct. And then there's one other possibility. That's this one. Probability that you don't get any correct. So if I want to look at the probability of at least one correct, should I calculate the probability of 1 correct plus the probability of 2 correct, 3 correct, 4 correct, all the way up to 10? Or is there a different way I can calculate this probability? Something that might be more efficient.
The probability of
complementary rule.
that you got one wrong.
Yeah, use the rule of complements. So 1 minus the probability of, how would you say that? How would you describe it?
Wrong.
Yeah, no correct answers, or none. And the advantage is there's only one probability to calculate here, whereas over here, there'd be 10 probabilities to calculate. So probability of no correct answers. Correct answers. Well, let me let W1 be the event. The first answer is wrong. And so on. W1, W2, W3. In fact, the probability that you have no correct answers is really going to be this probability. Probability of W1 and W2 and all the way down to W10. All 10 of those are wrong. Here's the thing. You're making guesses on these probabilities, or you're making guesses on these questions. And so the probabilities involved are going to be independent events. So if the probabilities are involved or independent, then I can write that as a probability that the first one is wrong, times probability that the second one was wrong, all the way down to the 10th one being wrong. Now, as a quick reminder, each of these questions has 5 possible answers, only one of which is correct and 4 of which are going to be wrong. So on any one question, what's the probability of getting one wrong?
4 out of 5.
4 out of 5. So overall, I get 4 out of 5 to the 10th power. That's not my final calculation. I need to calculate
Do 1 minus.
1 minus that, yeah. So thank you. I need to do 1 minus 4/5 to the 10th power. And there should be a pretty good chance, about an 89.26% chance that you get at least one right. Yay. And that's it. Okay. Do be careful spending some time on this. These are going to be probably some of the more challenging problems you're going to run into in probability, but there's plenty of help. Reach out and get some help if you're struggling.